I am Anush Martirosyan, representing a company called 2Hertz. We are working on audio processing and speech enhancement algorithms. We use AI to build our algorithms. So I'm going to talk today about one of our algorithms, which is the most important one throughout the life cycle of our company. It's a noise cancellation algorithm that we have developed over past 2 years. Can we switch the lights off, please? Okay, thank you. So, as I said, I'm going to talk about a noise cancellation algorithm, which means that today we are going to talk a lot about the noise, different kinds of noises, loud noises, annoying noises, and etc. I imagine that every one of us have been in a situation that you need to do an important call and you are in a noisy space. For example, you are in an airport and you need to do an important call for you. You are at home, working from home, and your baby is crying in the next room. Or you are just in office. Nowadays, all the offices tend to be open space, which is quite good. It's too nice. There is more air to breathe. But the problem of open air offices is the noise. So if you need to make a call, just a regular call or a meeting with your colleagues, you will try to find out a silent place to make that call possible because the environment is too noisy. Imagine there were a button which allowed you to mute the background noise entirely. In real life, I imagine 3 levels of this button. You do this in real life, like you're sitting in a cafe, it's too noisy, you have a button, you turn it on, and all the noise is gone, and you are in a silent place. The second level, lower level, is when you are able to mute the background noise in some calls, and you mute everything except your voice. For example, if your colleague is talking in the next desk, his voice is not passing through the algorithm, through the call, and only your voice is passing. This is kind of personal noise cancellation, that an algorithm that recognizes your voice and removes all the other things around. And the third level, one level lower, is an algorithm that will recognize human voices and noises and suppress everything which is called noise and keeps everything which is called the human voice. I will go through these levels from the bottom side to the upper side. So imagine you have some background noises data set and some human voices data set. In order to be able to distinguish, to make machines distinguish this kind of audios, it is important to have some principal structural differences between these two, right? Because machine can recognize only structural differences. If they are very, very similar, machine can never learn the difference. So if we think about the sound, the human voice and the noise, we need to find, and we want to distinguish these two somehow, we need to find a way to distinguish some principal differences between these two. The first thing that we may want to look into is the waveform of the audio file. That is a representation of audio file, the amplitude versus time representation of the audio file. I brought here 3 examples of waveforms. One of the examples is a clean speech of a human. One is a noise, and one is a mix of these two. Which is like a recording in a noisy space of the same human. So what do you think, which one is the mix, the worst one? The middle one?
Might be the first one.
Who thinks that it's the middle one? Okay. Some people. Noise and human. Look, one of these images is for clean speech. I guess you can imagine that it's the third one because there are some silence intervals. But which one is the noise, pure noise, and which one is the mix of the voice and the pure noise? Is a mix? Okay, that's not true, and that's because the amplitude doesn't matter too much. It's not visible from the images representing the waveform, and even humans can't recognize the amplitude of the speech. We recognize not the amplitude, but the differences of amplitude during the time. And in that sense, spectrograms, which are which are visualizations of these differences of the amplitude over the time, are more informative. From this picture, it's more clear that the third one is again the clean speech. The middle one is the noise, and the first one is the mix of the speech and the voice. Here it's more clear and more visible. And in fact, this is the main way of distinguishing the noise from the voice. As you can see from this picture, and I will show more now, the human speech has a structure. There are some peaks and repeating peaks for the human speech. Noise doesn't have any structure like this one, and the upper one is the mix, so you will have some structures, but lots of noise in the middle. Here I have brought some examples of noises. As you can see, as I said, noise doesn't have any structure, like these two in the bottom side. But sometimes noise may have very, very artificial structure, like the first two. The first one is a beep, like beep, beep, beep. It's very artificially structured thing. And the second one is a siren that you can hear from the ambulance or the tornado. It looks like this. It's again very, very artificial. It has a strict period, etc. As I said, human voices are very similar between each other. They have a concrete structure, and these are some spectrograms of different people, male and female, and you can see that there are some patterns here. And this is exactly what we are trying to teach the machine to learn, these patterns. And where the machine sees the patterns, it recognizes it as a clean speech. Where there are no patterns or very artificial patterns, then it's a noise. So giving this, teaching the machine to recognize the speech and the human speech in a noisy recording, it can be trained like this. We have different noises. We have clean speeches. We mix them up to get noisy recordings for the clean speech, and we feed it to the DNN. And we expect to get clean speech as an output. So as an input, we give a mix of a noise and the speech. And as an output, we give clean speech, some features of clean speech and some features of the mixes. And that features are very, very based on the spectrograms that I was showing you in previous slide. And for the inference, you can imagine it like this. You have an audio frame. You can't do the processing on entire file. You have an audio frame, a small piece of the file. You do some signal pre-processing on it to get some important features that the machine can see and recognize, like some features that are based on the spectrogram. You pass it through the neural network. Then you do some post-processing and get noise-free audio frame. Then you concatenate these audio frames in a special manner that is very familiar for signal processing guys. And you get a noise-free audio frame, end-to-end. Okay. The most important, not the most, but one of the important parts of the AI is being able to measure the quality of your product or of your algorithm. If you don't measure it properly, you will never end up with a good solution. So how to measure the quality of noise cancellation algorithms in general? The most reliable tests are subjective tests. It's kind of giving some audio files, before and after audio files to some people, some group of people, and getting their feedback. If most of them, and evaluating it somehow. If you want to compare two different models, then you need to give first model to the group of the persons, then the second model. And of course, you can't be limited in a. You need to be to have a big data set to cover as much cases as possible. For example, different noises, different noise levels, and etc. And as you can imagine, these kind of tests are very, very expensive because you need to hire some persons that need to be qualified for doing subjective tests. They need to be listening to hours of speeches and audio files and do the evaluations. It's even known that the mood of the person is affecting the results. For example, if you are doing subjective tests in the morning and the same person does it in the evening, they can give completely different results. So there are special techniques of doing subjective tests that are too expensive. In this proposal, there are developed different algorithm objective evaluation measures. These algorithms are designed to simulate how would be the results if a group of persons were subjectively testing the algorithm. In academic world, objective evaluation measure PESC is used, but after using it for a while, we have understood that it's not designed for our case. It's for measuring some degradations of the file going through the network. So we have studied other algorithms. We have got two more, Polka and TreeQuest. Polka is kind of an upgrade for PESC and again doesn't do the job that we need. But the TreeQuest is just right for measuring noise cancellation algorithm. But the problem is that all these evaluation metrics are designed not for algorithmic tests, but for device tests. Imagine you have implemented a noise cancellation algorithm on a device, and you want to measure its performance. So far, there is no known evaluation metric that will allow to do algorithmic evaluations for the algorithms. But these two, TreeQuest and more or less Polka, are good enough if you are using a special kind of test data to use that evaluation metrics. In fact, I have bought some images of heads, so-called heads, which are head and torso simulators. And for doing tests that meet the specifications for device tests, you need to have an audio lab, like shown in that picture, where there is a human simulation, a human-sized guy like this, who has an artificial mouth, who is supposed to pronounce the speech, well, play the speech, and who has artificial ears that are listening or recording the environmental audio.
Can I ask you, did you really use this type?
No, we don't use, because it's designed for device-specific tests. But we are not doing something which is device-specific. Our algorithm is working on any devices. We have some recordings that are done in a company, Head Acoustics, in Germany. They have this kind of audio lab, the most equipped with the most recent equipment. We have recordings from them, and we use these recordings for our tests. By the way, this company is the company who who invested this evaluation metric called TreeQuest, which is exactly for noise cancellation testing, device-wise. And in the specification, you will find lots of images like this that describe where to put the heads, what should be the dimensions of the audio lab, how to position the device under test, and etc. So let's go. Okay. Now let's talk about a little about the evolution of our algorithm that we have designed. We started 2 years ago. Only 2 people were working on it. They have approximately no imagination. This was a new field for them, but the idea was very, very interesting for them. So they decided to try out some AI to clean the noise from the audio files. They have started with very simple DNN. They had a very few data, which was not good at all, I can say. They were the audio files were narrow band. It's a term that describes the quality of the audio. It's the very lowest quality that is worth to work with. And they were testing all the results only subjectively on a very few test data, which were including very, very annoying noises. And in that, it was doing a noise cancellation. When we look back now, the algorithm was very bad. It was corrupting the voice very much. But that's good that we didn't realize it that time, because we wouldn't continue working on it if we realized. But as it was doing a noise cancellation, it was decided to continue working on it. And the first step towards getting a good model was working on the data set. We have achieved lots of human speeches. We have achieved lots of noises. I mean, you can imagine 2,000 people's recordings for 2,000 people and more than 10,000 noises. And we, with all the team, have listened every single file in this dataset to make sure that it's accurate. There are no noises in the speech files, and noises are good enough for the training. So we have got a big enough dataset which allowed us to move forward. Then we worked on improving the model structure. We started to use not simple DNNs, but some kind of mixtures, RNN networks, and etc. And at that time, we decided to have more structured data set, which will allow us to compare different models. And at that time, we were using only PESC, which, as I told, is not designed for our case. But in fact, it was mapping somehow the quality that we were subjectively listening to the audios and the evaluation metric numbers. The higher the number, the better the quality, and it was mapping somehow. Then the next step was going from narrowband audio files to wideband. It's kind of having 2 times more data to feed to the network, which led us to do some optimizations to be able to train the network in reasonable time. And we also worked on changing some architectures. We have come to GRU cells and etc. and have got another good model which was working for wideband audios. Now at this moment, we were still using PESC. And I want to mention that using this evaluation metric that wasn't designed for our case helped us very much to improve the quality, because it was mapping somehow. Then we have the last changes that we are doing on the model are doing some simulations of codecs, of network, of room reverberations. It's kind of the reverberation that comes from the room, and you feel where the person is sitting in the room. It has a huge impact on the algorithm quality as well. And simulations of different microphones. Okay. And we already started using this matrix request, which is better describes our case. As I mentioned, the company Head Acoustics we have a project with them. We have passed the test project. They have tested our algorithm and provided us with the results. And this is one of the results that I want to share. As you can see, in the industry, the acceptable quality is this red line, and the premium quality is the blue one. As you can see, we are above the premium quality line, which was very good news for us, because when you are evaluating yourself and wow, it's a good technology and it's different, and when other people are measuring you and giving such a result, it's another story. Okay, so the latency constraints are also very important in order to be able to integrate the algorithm into a product. In the industry, latency constraints are 200 milliseconds. I don't want to go deeper here. Our algorithm introduced only 20 milliseconds of latency to the overall path, which is quite good result. This noise cancellation is interesting by itself. It's already integrated in our app, and thousands of people are using it and cleaning the noise. And also, I want to mention that this product has become a product of the year last year, and my colleagues are going to have a talk about how that happened. So if you are interested, you can attend the talk today at 5 p.m. As we go to the customers and learn feedback from them, we get some kind of very wired requirements. For example, one of the customer wants to keep the music. One of the customer treats the music as non-noise and wants to as a noise and wants to remove it. Expectations are very, very different. The most funniest thing that happened to us recently is from call centers. They were arguing that our algorithm is removing human screams and yelling because the customers were calling to them and screaming to them, and our algorithm was cutting these screams. Well, from our perspective, it's a feature, but they needed these screams to be passed. And in order to design a new model that passes the screams, we needed the data. And over the week, we were screaming and yelling in the office to record all this stuff and to use as a data. Okay. So the next level, as I mentioned, is personal noise cancellation, when the algorithm passes only your voice and removes all the other humans' voices. As you saw, the human voices are quite similar, and it's not so easy to distinguish two different people's noises, but we have achieved some results in this area too, and I hope that in the near future we will provide a new algorithm to the customers that will provide personal noise cancellation. We have used transfer learning, multitask learning. We have the individual data collection for that. We have designed a special algorithm that will allow us to decide if this part of the recording is good enough for using in our trains or not. It is predicting the noise level in a noisy audio file. And we are designing special test set for individuals to be able to evaluate the results on that. Regarding the first point that I mentioned in the beginning, a mute background noise that you can use in real life, I don't have it. So only mute background during online conversations where I can put my algorithm. Okay, that's all from me. Any questions, comments? Yes.
You have 5 minutes to ask questions, right? I just wonder how do you get permission for your application to get the data of other applications like Skype or phone calls? Isn't that private?
No, that's not private. We are sitting as a driver into the application, and we get the data from the microphone. And all the processing is done on a user's local machine. Nothing is going to the servers and backward. Yeah. Well, as I mentioned, we have some recordings that we ordered from the head acoustics. We also generate some artificial taste data for our tests.